are exactly. So a force is a type of interaction between two objects that affects their motion in some way, so they can cause accelerations, cause transfers of momentum between objects. And physicists recognize so far four different types of fundamental forces: the gravitational force, electromagnetic, and the strong and weak nuclear forces. But usually in a first year physics class, we will categorize forces a little bit differently, so I want to go over that. So in this class, we'll be categorizing forces, first of all, separating them into two broader categories. So one would be non-contact forces, which we could also describe as long-range forces. And these would include the gravitational force, and then also electric and magnetic forces. And in a first year mechanics class, we're not really going to talk about electric and magnetic forces, but we will talk a lot about the gravitational force, which is just a force of attraction between any two objects with mass. So, apart from the gravitational force, we have a number of forces that we can categorize as contact forces. So, as the name implies, this requires there to be direct physical contact between the two objects that are interacting, and there are a handful of different types of contact forces that we will deal with. So, first of all, anytime there are two surfaces in contact with each other, those two surfaces will push against each other in a direction that is largely perpendicular to the surface, and we call these normal forces. And the word normal is just being used in its mathematical context where it means perpendicular. The other type of force that can act between two surfaces is friction, which is a force that can act to oppose sliding between the two surfaces. So some surfaces will be modeled as frictionless in this class, but we also will spend quite a bit of time talking about friction forces. If we have any kind of rope or string that is being used to pull an object, we label that force as tension. And usually in this class, at least until we get to rotation, we will assume that anytime you have a rope or a string or a cable under tension, it applies the same force at both ends. And tension is always a pulling force, so a rope cannot be used to push something, only to pull. And then sometimes we will have springs involved in some physical scenario, and springs can exert either tensile or compressive forces, so we kind of put those in their own category. And there are others as well, but this is a good starting point for now. So one thing we want to be able to do in this class is to identify and diagram all of the forces that act in some situation and create something that is called a free body diagram. And these are extremely common and indispensable tools that physicists will use. And sometimes they can be a little difficult to create. So I want to go over a sort of intermediate step that sometimes students can use to help them draw a free body diagram, and that is something called an interaction diagram or a system schema. I think in the Randall Knight textbook, these are called interaction diagrams, which are not introduced until chapter 7. So let's say we have a scenario, just something really simple like this, of an apple sitting on top of a book, sitting on the ground. And I want to know, what are all of the forces that are acting on the apple and acting on the book in this scenario. So what I can do is draw a sort of cartoon diagram, and this is, again, called an interaction diagram or a system schema. So the first thing I'm going to do is I'm just going to list all of the objects that seem to be involved in this scene, and they're sort of already labeled here in the picture for the most part, but off to the side I'll just draw maybe a bubble with the word apple in it, and then we've got a book, And then we also have the Earth here, but I'm actually going to draw that as two separate objects. So I'm going to have the Earth as one object that is certainly taking part in the scenario, but I'm going to list the ground as a separate object here. And the reason I do that is the Earth will be able to exert gravitational forces on objects that are not touching it. But the ground, which is sort of part of the Earth, can exert other forces if and only if it is in contact with the object. Okay, so what we do next is we draw lines between all of the pairs of objects that are interacting in some way. So the Earth can interact with anything through the gravitational force because it is long range, it does not require contact. So I can connect the Earth to, well, technically the ground is part of the Earth, so I could leave that line out if I wanted to. But it's going to be interacting with the book and the apple. In fact, yeah, I'll take this line out. So these lines represent gravitational forces. And one thing I will point out is there are no arrows on these lines, so there's no directionality implied here. And that can actually become important when you're studying Newton's third law. Okay, and then as far as the other objects go, the ground is only touching the book, so it is in contact there. And then the book is also in contact with the apple, so there's an interaction there. Another thing I can do is I can label each of these lines if I want to indicate what type of force is being shown. So for the two lines connecting the Earth to other objects, those would be gravitational forces. So one notation I could use is I could write just F sub g for force of gravity. Between the book and the ground, that's a case where we have two surfaces in contact, so I would call that a normal force, the book and the ground sort of pushing against each other. So I could label that F sub n for normal force. And then likewise with the apple and the book, we have two surfaces that are in contact, so I could call that a normal force as well. Now, in this case, there's not going to be any friction forces involved because there's nothing that is trying to make these surfaces slide against one another. But if there were, I would draw a separate line between the two surfaces to indicate a friction force was acting at that interface as well. Okay, so the next thing I do is I'm going to try to draw a free body diagram for these objects, and that's what we are really ultimately after in this exercise. So I'm going to start with the book, and maybe I'll add some color coding here. So the book is kind of orange in our picture, and the apple is sort of red, so I'll use those colors for my diagrams. All right, so for the book, when you are making a free body diagram, the first thing you always do is just place a dot somewhere on your paper, and that dot indicates the object. And then I'm going to draw arrows pointing away from the dot, always attached to it, where every arrow represents some force that is acting on that object. So I can look at this diagram that I've drawn and count the number of lines that are connected to the book, and that tells me how many forces I should end up drawing. So if I just go through these one at a time, I have a gravitational force here. So that's an interaction between the Earth and the book. Gravity will attract two objects, so the book is being pulled towards the center of the Earth. So I can show that as an arrow pointing straight down on the page. And I'll label that force of gravity, and I'm going to add a longer notation here. I'm going to call this the force on the book by the ground. I'm just going to abbreviate the objects here, but this notation is also really, really useful for helping you to get a grasp on Newton's third law, so I recommend using it at least early on. And then in addition to this, I have two normal forces being shown. So one is between the ground and the book, and one is between the apple and the book. So what's happening here is the earth is going to be pushing up on the book at this interface here, but then the apple is going to be pushing down on the book over here. So there's going to be two additional forces acting. So I'm actually going to draw the force from the apple pushing down on the book first. Anytime you have two forces pointing in the same direction, you want to kind of squeeze those together like this. So I'm going to call this force normal on the book by the apple. And then I need to show the upward force from the ground. Now, something I know about this book is that it is not moving in this scene, and the way the forces are balanced over here is going to tell me ultimately something about how the object is accelerating. And I have not covered Newton's second law in this video, but just real briefly, if an object is not accelerating, then the forces acting on it must be perfectly balanced. So if I look here at the forces I've drawn, I have one force that's sort of 3 squares long pointing down, another one that is 2 squares long pointing down, so it's a total of 5 squares or 5 units of force acting downward on the book. So I need 5 units of force acting upward as well. So all of that force in this case has to be supplied by the ground. So my remaining force is going to look like this, and I'll call that force normal on the book by the earth. So that's it. That would be the full and complete free body diagram for the book. If I want to do the apple is actually going to be a little simpler because there are only 2 forces acting here. I've got this line here representing the gravitational force from the earth, and then this line here representing the normal force from the book, which is going to be pushing up. So the apple's being pulled down by the earth, and then it's being pushed up from below by the book, and those 2 forces are going to end up being balanced as well because the apple is also not accelerating. So I'll draw a dot to represent the apple, and then I'm going to draw first the normal force from the book. So it's going to be force normal on the apple by the book. And then there's going to be a gravitational force from the earth, which is down. So call that force of gravity on the apple by the earth. Now, when you study Newton's third law, you will learn that Newton's third law states that any 2 interacting objects will exert equal and opposite forces on each other. And in this diagram, every line I mentioned before does not have a directionality to it. Each line represents really a pair of equal and opposite forces, one acting on each object at the end of that line. So in this case, we actually see up here a downward force, which we called force normal on the book by the apple, and then we see an upward force that we labeled force normal on the apple by the book. These 2 forces are taking place between the same 2 objects, the apple and the book. They point in opposite directions, and I also knew to draw these equal in length because these are a pair of forces that are actually related by Newton's third law. So that was the only way I knew how to draw these forces relative to one of the forces in the other diagram. Okay, so let's look at one more example and then wrap this video up. So if I have a somewhat more complicated situation, let's say a person is pushing 3 crates across the floor, and I want to know, what are all of the different forces that are acting here. So to make a system schema diagram, I've got 3 crates here, A, B, and C. I've got a person who is pushing these crates, and then they're all moving across some sort of floor or surface. And then the earth is certainly going to be exerting some influence here as well. So as far as what is interacting with what, the earth is going to be exerting gravitational forces on everything here. And again, whether or not I want to connect it to the floor or consider the floor as really being sort of firmly attached to the earth and part of it, that's not super important here because I'm just going to be focused on the forces that are acting on maybe these objects up here, maybe even really just the three crates. So as far as any other interactions, remember only contact forces are allowed here. So for instance, I cannot say that the person is pushing crate B or crate C because they are not in contact. The person is only in contact with crate A, which they are pushing. Let's call this a normal force. These are all gravitational forces. And then the person is also standing on the floor. So I guess that would also be some sort of normal force. Sometimes people will use terms like force applied or something else to refer to active forces from, say, a person pushing on an object. So it doesn't really matter what we call it as long as we can identify it and know something about its direction. All right, crates A and B are in contact with each other and also the floor. And again, I could call this force between A and B a normal force. I could call it maybe a contact force. I'll just call these all normal forces. And then B and C are in contact with each other, and C is also in contact with the floor. All right, so there's a lot more going on here, and this is without even considering friction. If there was friction between the crates and the surface, I would need a few more lines connecting the boxes to the floor as well. So there's a lot going on here. Okay, so let's see if I can construct a free body diagram for crate A. So if I draw a box around A and count the lines, I see 4 forces on the diagram touching A. So I know in my free body diagram for object A, there should be 4 arrows ultimately. So I see a gravitational force from the Earth. So it's called on A by the Earth. And then there are 3 normal forces or contact forces. One is coming from the ground, which is going to be pushing up on it. One is coming from the person, which is pushing to the right. And then at this interface here, again, at interfaces you can only have pushing forces. So B is going to be pushing A in this direction. So we have normal forces kind of going in all 3 of the other directions. The normal force on A by the floor points up, and that has to be balanced to the gravitational force since the box is not accelerating in the vertical direction. Now we don't actually know what's happening in the horizontal direction here. The person could be pushing the boxes at a constant speed, or the boxes could be accelerating. Let's suppose everything is sort of speeding up to the right here. So there's an acceleration in this direction. That means there has to be an excess force in that direction acting on all of the objects. So I'm just going to sort of arbitrarily draw a force from the person, maybe like this, let's say 6 squares long. Force normal on A by the person, and then B has to be pushing backwards, but with maybe not quite as much force. Let's just make this 4 lines. I'm going to call it on A by B. All right, so next, let's look at crate B. And there are, again, 4 forces acting on B. There's going to be a gravitational force. Doesn't necessarily have to be the same length as the one acting on A. Maybe box B is a little bit smaller. And then we'll have a normal force from the ground on B by floor. So now in the horizontal direction, there's going to be box A pushing B to the right this way, but then box C is going to be pushing back to the left. Now for the force pushing to the right, I know that box B is pushing A to the left at this interface with a force that I've drawn 4 units long. Newton's third law says that A will be pushing B in the opposite direction with exactly the same amount of force. So I need a force pointing to the right that is also 4 units long. And I'll call that force on B by A. And then box C is going to be pushing backwards with, again, a force that is not quite as strong as the one pushing to the right. So let's call that force normal on B by C. All right, and then finally, box C. So there's going to be a gravitational force on C as well. And again, we don't have any information about how large or massive these boxes are, so I'm just going to make up a number. All right, so this is force of gravity on C by the Earth, and this is force normal on C by the floor. And then, looking at this diagram here, there's only 1, 2, 3 forces this time going to object C. I've got 2 of them already, these 2. So the only one left is the force between B and C. So box B is going to be pushing box C to the right with exactly the same amount of force as box C is pushing B to the left. So I drew that arrow 3 squares long over here. So I've got to draw it the same length over here. So that is force normal on C by B. All right, so those are my free body diagrams for all 3 boxes. Now, those of you who know a little bit more about Newton's third law can do the math and figure out that I haven't actually drawn this accurately in terms of matching the net horizontal forces to the masses of the boxes. So I'm not really worried about that too much yet. This is really just a qualitative exercise just to show you how to identify and label all of the forces. So we should be able to come up with free body diagrams that have this many forces in the appropriate directions for each of the boxes. And we do want to recognize when we have pairs of forces across these diagrams that are related by Newton's third law and which must be drawn equal in length. Okay, so I'll try to show maybe more complicated and more quantitative examples later, but I think this is enough for now, so thank you all for watching.